camera for the live stream, and you saw my head the whole time.
We have to be careful now, so you can have a microphone in this way.
To celebrate this 30th anniversary of the Montreal Protocol, which is considered to be the most successful protocol for the environment. And to celebrate this, we have a program that will cover the various parts of the protocol, from the ozone science to the effect, its effect on climate, and how the protocol has help also the climate, the governance of the protocol. So we'll have all this broad range of presentation, and I think it's going to be very interesting. And so at first I would like to give the floor to the Ministry of Ecological and Solidarity Transition, Mrs. Marie-Laure Rézélier, please.
It's a great honor for me to introduce this symposium with such a prestigious assembly. And first, I wish to thank the organizers of this symposium, in particular, Madame Godin Beckman from the Observatoire de Versailles à Saint-Quentin-en-Yvelines, the International Ozone Commission, and also Frank l'Académie des Sciences, la Fondation David Lucas, for facilitating the practical arrangements and hosting the meeting. I also welcome, in the name of the French Ministry for the Environment, Nicolas Hulot, all the attendees. A few days after the World Ozone Day and a few weeks before the joint event meeting in the Conference of the Parties to the Vienna Convention and 2019 meeting of the parties to the Montreal Protocol that will celebrate the 30th anniversary of the Montreal Protocol, I would like to come back to its history. Adopted in 1985, after the hole in the ozone layer was discovered, the goal of the Vienna Convention is to promote the scientific cooperation between its parties by means of cooperation and of harmonization of the policies, the systematic observations of the ozone layer and research programs, as well as information exchanges. The Vienna Convention does not force to take measures to regulate ozone-depleting substances. The Montreal Protocol was consequently elaborated to serve this goal and was signed in 1997 by 24 parties, including France. The Convention and the Protocol are universally ratified. Quasi 200 parties. This is important and demonstrates the trust that countries put into this protocol, yet a demanding one. Since 40 years, this constructive and ambitious ambience gathering all the countries, the developed and the developing ones, the civil society, the implementing agencies, and the industry have always been an important characteristic of the protocol and the convention. The Montreal Protocol is recognized as one of the most effective environmental instruments. The Montreal Protocol is a success. Thanks to our collective action, it has already achieved 98% of its goals. These results demonstrate that an environmental global action is possible and effective. The ozone layer is recovering, and it is estimated that the global ozone layer should return to its pre-1980 levels by around 2060. As said Catherine McKenna last Friday in Montreal for the birthday, the Montreal Protocol is a leading example of successful partnerships between government, experts, and citizens in order to address the greatest environmental threats of our time. The ozone layer protects the Earth from the extraterrestrial UV irradiation. The Montreal Protocol has huge benefits regarding human health and environment because 20 million of skin cancers and 130 million cataracts have been avoided with its implementation, and it also contributed to conservation of the harvest of the aquatic plankton. Furthermore, because of the ozone depletion substances are also greenhouse gases, this protocol also avoided the emission of 135 billion tons CO2 equivalent, which is more than the Kyoto Protocol did. The Montreal Protocol success is due to its principle and institution. The parties rely on scientific probes, which allows to take well-informed decisions, a differentiated approach between the developed countries and the developing countries, allowing to take into account the world situations, effective institutions, in particular the multilateral fund financing the project to help developing countries to reach the binding goals of the protocol and the implementation committee. I want to underline the importance of the technical and scientific data in the smooth running of the Montreal Protocol. Indeed, it is thanks to scientific progress and observation, but also to the good knowledge of the available alternative technologies, that the protocol was not only created, but also that it evolved over time with amendments and adjustments in order to guarantee the achievement of its goal of the protection of the ozone layer to protect the human health and the environment. The French Ministry for Environment, which I represent today, contributed several times to the Trust Fund for financing activities on research and systematic observation relevant to the Vienna Convention, and in particular in 2016 and this year. This marks the dedication of France on this matter and its will to support the research of the ozone layer, including training and capacity building in countries meeting the criteria of the Article 5 of the protocol. The parties to the Montreal Protocol, together with the scientific community, but also in connection with the industry, which is the first one concerned by its requirements, have always surpassed the various challenges when they appeared. But the latest challenge, but not the least, relates to the hydrofluorocarbons. Some of the solutions developed by the industry as an alternative to the ozone-depleting substances, the HFCs, turn out to be powerful greenhouse gases, and as you already know. Without any action, HFCs could have represented 20% of the world greenhouse gases emission in 2060 and 0.5 degrees of global warming in 2100. We couldn't accept that by fixing a global environment issue, our action contributes to worsen and overwhelm. In order to act against this climatic threat, the parties of the Montreal Protocol adopted the Kigali Amendment on the 15th of October 2016 during the 28th meeting of the parties. The well-proven expertise of the Montreal Protocol, notably regarding the refrigeration and air conditioning sectors, and its robust financial mechanism, were indeed the best suited tools to ensure a quick decrease in HFC emission. This amendment, which France and the European Union supported for several years, is the greatest concrete action to reach the goal of the Paris Agreement to limit the global warming since the agreement was adopted late 2015. The adoption and the early implementation of the amendment was one of French priorities at the COP21 president. It consists in the progressive phase-down of the production and consumption of HFC, and it should avoid approximately 80 billion tons CO2 equivalent until 2050. This amendment demonstrates once that we know how to reconcile ambition and solidarity with a common objective: protect our climate, while ensuring the sustainable development of all the countries. Furthermore, the Kigali Amendment gives worldwide a clear signal to the industry to speed up the development and the distribution of zero or low global warming potential alternatives. This amendment must now be ratified to enter in force. The procedure of ratification by France is already underway. The national law for ratification will be presented in the Ministerial Council, and its adoption by the Parliament is expected for this autumn. As you know, the European Union is one of the more advantaged regions regarding the phase-down of HFC, with the adoption in 2014 of an emission regulation of fluorinated greenhouse gases, Regulation EU 517/2014, which aims to reduce 79% of the HFC's consumption in 2030 compared to 2015. Thanks to this regulation, the requirements of the Kigali Amendment are already covered at the European level. It is, however, a significant effort for the member states to the European Union, but we are definitively confident that the current innovations and the currently developed technologies will allow us to reach it. The French Ministry for the Environment is consequently acting to inform all the stakeholders and to favor the deployment of the HFC alternatives, mainly in the refrigeration and air conditioning sectors. Our action consists notably in the following: inform and aware companies on the economic and strategic challenges of a fast and complete transition to zero and low global warming alternatives. Provide training to the actors, mainly the operators, and the new alternative technologies. Technical and or financial support for the suppliers of innovative solutions, with calls for projects to help the development of air conditioning and refrigeration equipment working without HFC, and of course without ozone-depleting substance, and even without any coolant. Several of the project's prize winners are moreover designed to work from solar energy or to value the wasted heat. To conclude, I wish you fruitful discussion during these 2 days, which will for sure enrich our strengthened and collective concomitant to act together to protect the ozone layer and the climate. And thank you very, very much.
Thank you for emphasizing the universal success of the Montreal Protocol and its universal ratification and the support of the ministry. And now I will give the floor to Marie Chana from the Academy of Science. Dear colleagues, and for many of you, dear friends, it's a pleasure for me to welcome you to this nice place from under the office of the Académie des Sciences, because this foundation replica is the property of the Institute of France, and it's often put at the disposal of such symposium. So I hope that you will enjoy the place and will do a good job there. Obviously, the permanent secretary of the Académie des Sciences, Catherine Béchina, will have liked to speak to you today and welcome you. But today is the opening day of the academic year at the Academy. She couldn't miss that, and she asked me to convey her best wishes for a successful meeting. But I'm happy that it gives me the opportunity for myself to present you also my best wishes for success, because I think that the 30th anniversary of the Montreal Protocol needed such a celebration, and I think we are in a place to do it. And I see the faces of many of you who have worked on this issue for many years, now almost 40 years that we are on the subject, and happily there's some young ones who joined the group, but I recognize many faces. So I really want to tell you also that the Académie des Sciences has followed the issue of the ozone layer for all along trajectory, and the Academy has published several books dealing with the issue. The first one dealt with the ozone, tropospheric ozone. The second one, which is a big issue, was published in 1998 and led by Gérard Mégide. And since there were two more ones, one on the impact of aircraft on the environment, which I organized, and a very recent one, which is smaller because it's a summary, is l'évolution de l'ozone stratosphérique with Sophie and Cathy, which I led. So these books are in French, which will not please most of you, but they are available for the French-speaking people. I will put the copy outside so you can have the address of the editor if you want to order them. The Academy obviously is following in the Committee of Environment what's going on with the ozone, and we discuss the issue each time something is happening. The Academy is also offering the possibility of publishing the proceedings of this meeting, if we decide to do so, in a special issue of Geoscience, which is an issue of the Note compte rendu de l'Académie. So I was the precision with Sophie Arzo in the discussion of what is needed to be published in English, not in French. We will talk in this meeting. So I also want to present my apology for the CNES, the French Space Agency, who couldn't be represented today because there's a change of position of the responsible of this discipline, of our discipline. But I want to thank them for the support of this symposium. But I think it's important to mention them because CNES was very important on the ozone issue. It was working with NASA and ESA on the main satellites, URs, ENMISAT and so forth. But I think the main thing that it did is really to put at the disposal of our community those stratospheric balloons that played a very major role in interpreting processors and then the Arctic issue. And also of the superpressurized balloon, which played a big role in Antarctica, in the Volco and
So I think CNES has been playing a major role, but this will be described in much more detail this afternoon by John Pyle and Jean-Pierre Bobo, so I won't say more about it, just to encourage CNES to go on doing this kind of work, for which it was important. So in concluding my remarks, I'm happy to describe what we have this afternoon. You have the programming a little better than me, so I wish for all of us a good meeting, and also a good stay in Paris. Tomorrow it will be sunny, so maybe when you are reviewing the garden as coffee break, it's very nice. Thank you. Thank you, Marie-Lise. Yes, the support of the Academy of Science is really appreciated in this space. Really nice. So now I will leave the floor to Hervé Lepreut, who is the director of Montreal.
Okay, thank you very much. I guess some of you do not know what is Institut Pierre Simon Laplace. So yeah, just a few words to begin with this. It's a federation of laboratories working mainly in climate issues, also for climate of other planets in the Paris area. So together there are 9 laboratories and more than 1,000 persons working on these issues. What relates it strongly to this anniversary is the fact that it was created by Gérard Mégy, and it was created a bit after the 30th anniversary. I think there is something like 25 people, 26, 27 years old. So in a way, it's a testimony of the fact that, and I'm not an ozone person. I will not discuss in depth the ozone issue, but I think what I could measure from my position as PSL director is that the ozone problem was the starter in the kind of networking that occurred throughout the scientific community, and I could visit the observatories, one in Patagonia, also my country, but it's just my wife, in La Réunion, in Provence, all these observatories, which are operated first by people from IPSL, they are testimony of this networking that occurred through the ozone problem and which has occurred afterwards for the climate problem. And I think in that sense, just as if we think of the community of our disciplines, the ozone has not only been a success, example of a success in terms of results, of impact on the society, but also an example in terms of organization, of joint organization of different laboratories, different disciplines. And I'm sensitive to that because I realized it a lot of afterwards, after it happened. When 30 years ago I was already a researcher in those fields, but I was completely unaware of the depths of the ozone problem. I heard about it. Many things happened just after that. We were reminded that, for example, IPCC was founded the year after. So just to finish this, I think there is in France, I've seen many persons when you go in the street that deny the reality of the ozone problem. Okay, nothing serious never happened. It was something invented by scientists. I've heard that many times from the mayor of my little city in the suburb of Paris, from many people. And in a way, it's sad for scientists, and it's maybe even dangerous because there is a need to continue the monitoring of the situation, to continue the support of the observatories I mentioned. So there is a strong need to continue science. But in a way, it's nice because it's a measure of the success. And I was thinking that maybe in 30 years or 28 years from now, there will be an anniversary for the Paris Agreement. I hope I can be there. It's not granted. But in a way, if people say, okay, this had been invented, there was never any real climate problem. It warmed up a little, but it's just not mixing, but it would be nice. Okay, so I stop here.
Thank you very much, Lee. So now giving the floor to Mr. Danu from the environmental program of the United Nations. Thank you.
Thank you so much. Good morning, ladies and gentlemen, distinguished colleagues, scientists. Really glad to be here in this great city, Paris, which made yet another great success 2 years back on the Paris Climate Agreement. And on behalf of Mr. Eric Soham, the Executive Director of UN Environment, now we call UN Environment because nobody knows what UNEP does, so we call UN Environment. This is our new name. So UN Environment basically is very proud of having been the part of the process as a member of the International Ozone Commission by linking the science with the policy and business communities, and by hosting the Ozone Secretariat. Starting from 2010, we have started celebrating our success by its global membership to the Convention and Protocol. And 2015 was the 30th anniversary of the Ozone Convention, the Vienna Convention, sorry. And this year is the 30th anniversary of the Montreal Protocol. But what I really wanted to congratulate and thank for is the science community. And it's the International Ozone Commission and our professors Stolowski, Cicero, and Molina, Roland, and those pioneers started the search of the ozone depletion substances in the 1970s, and the thousands, if not millions, of scientists behind them, and who, over time, have been making steadfast efforts in monitoring and assessing ozone layer, and urging proactively the policymakers and business community to take actions and in identifying substitutes for ozone depletion substances for industrial sectors as solutions. And this is a typical example of how the science would work for the environment and how the science would help us find the green solutions. And that is what I really wanted to celebrate and appreciate. Last year, parties to the protocol, I did the Kigali Amendment to the protocol for controlling the growth of substitutes of ozone depletion substance. Some are most very powerful greenhouse gases. And I was told, by fully implementing this amendment, we have the potential to bring the global temperature down by 0.5 degrees Celsius. When I searched for the scientific basis of this amendment, I immediately realized and appreciate the endure of Dr. Susan Salman. And she was then, back to 2005, the co-chair of the IPCC Working Group 1. And
What was the comment with the...
oh, okay.
It's back.
Okay, great. And she was the co-chair of the IPCC Working Group 1. April 2005, I remember we were in Addis Ababa, and that was my first meeting as the Deputy Secretary of IPCC. And we approved successfully the special report on ozone and climate, if I'm not mistaken. So, ladies and gentlemen, we have achieved a lot in the last 30 years. And much more needs to be done. course in the next 30 years, and some of my predecessors have already mentioned this. So first, in safeguarding the ozone layer, we need to ask whether our efforts put there are adequate to sustain it for longer term, and what needs to be done further. And then secondly, in terms of limiting the greenhouse gas effects of some of the substitutes for ozone depletion substances, how soon we could replace those substitutes with those of climate-friendly ones. And thirdly, how could we make the story known to the rest of the world, not only in terms of phasing out the ozone depletion substances or the global membership, but pretty much the Science Policy Business Consortium, as was presented to me by Dr. Paul Newman from NASA. And colleagues, ladies and gentlemen, 30 years from now, we may not be able to predict what we can expect from the advancement of science and technology, but we could and have projected the development scenarios in 30 years. And first, world economy will be 3 times of the economy today, from 70 trillion to $222 trillion. And the world population will be added by another extra close to 3 billion people, newborn, and the population of China and India plus. The bad news is that we have already reached our critical boundaries of the planet, our planet, the Earth, the ozone, the climate, the biodiversity, the biochemical circles. And we only have one planet. We got to sustain it by all means. But that's why we need to work together, starting from you, from the science community, to engage the policy and business communities, and to continue keeping our eye on the emerging and increasing threats to our life-supporting system, the Earth, and another eye on solutions. So you have made the case on science for solutions, and you will do so. I believe that you will do so in the future. And your environment will always be behind you. And my office, the Chief Scientist Office of your Environment, and also our Secretariat, Ozone Secretariat in Nairobi, will be your first touch if you want to contact us. So we'll serve you, we'll be behind you and support you. So finally, I would like to congratulate again the successful organization of this meeting. And I wish after this 2 days discussion here, you will charter a new route toward the future for this community. Thank you very much.
Thank you very much for these nice words. So we are now starting the session, and I will try to bring the okay, so we will start with a talk from Guy Brasler on the historical perspective of ozone. Yes, sorry. Sure. Just yeah. It was coming yesterday, so yeah.
Great. So, good morning to all of you. Of course, I'm pretty pleased to be here with this beautiful crowd of prominent scientists who have been playing a major role in ozone research in the last 10 years or so. I was asked to provide a little bit of a historical perspective on ozone research, and of course, it would take a long time to do that if I wanted to be comprehensive, and therefore what I'm going to do is really to highlight a few topics with the hope then I'm going to bring up a number of events or situations that you might not have heard much about it. So I try to find things that are pretty interesting. Not everything, but a few events. Of course, we should start every historical discussion by providing a bit of on the discovery of ozone, and you know that ozone was kind of mentioned around 1840 when the German scientists working in Basel in Switzerland, Schönbein, produced a report in the local Naturforschungsgesellschaft, so the Society of Physical Sciences, indicating that the electrolysis of water produced an odor of kind of a very strong odor. And what was interesting is that he discussed this issue with a colleague at the University of Basel. Professor Vischer was a professor of Greek, and who suggested to him, said, well, since it's an odor, it wasn't really thought at that time that it was a gas or any chemical substance, that maybe you should call this principle, that this odor, ozone, which means, of course, to smell in ancient Greece. But there was a lot of confusion at that time about what ozone was. A lot of discussion, and you will see it took many, many years to find out exactly what was the nature of ozone. So Schönbein believed that the odor was probably associated with a gaseous substance released by the fluid due to the decomposition power of electricity. On the other hand, also in Switzerland, Delarive suggested no, that the odor was probably related to particles of the oxidized electrode material, and Schönbein kind of responded that this was probably unlikely because the same odor was observed during lightning storms, thunderstorms, etc. So at that time then Schönbein started to develop measurements of what could be ozone, because he had noticed that ozone reacts with potassium iodide, and that was, of course, the basis for measurements later on. So there were very, very soon several competing theories. Schönbein was trying to identify what this gas was, and many hypotheses came. Chlorine was one of them, HO2 was one of them. But finally, it considered ozone to be a negatively electrified oxygen that must be then compensated by a positive component, and this positive component was called end-ozone, and then oxygen, O2, was really the addition of ozone and end-ozone. Now, Sauret, also in Switzerland, considered that, no, ozone appears to be an allotropic form of oxygen, and he started to talk about oxygen dioxide or bioxide of oxygen, and there was a lot of discussion that took place at that time. But the concept of end-ozone came up as a very important aspect. End-ozone, positive state of oxygen, and Meissner in 1863 discovered that if dried electrified oxygen passed through moist air, mist is formed, a substance that then he called atmosone, which was then later on believed to be identical to this end-ozone. And end-ozone was believed, for example, to be the causes of cloud in tobacco, smoke of chimney, gunpowder, and so on. And in fact, Meissner was even able to build an instrument, an apparatus that would produce end-ozone. You can see how far we had been. So there was a lot of confusion about what ozone was, and this confusion can be seen in the letters that Schönbein and Faraday were exchanging. There is a book that I recommend you read, the letters between Faraday and Schönbein, and Faraday gets very, very confused. It just says, well, the confusion, he's talking about the confusion of the point that ought to be remembered in this issue, the difficulty of remembering from the reading of one letter to the other, what facts were in the former letter, and he concluded saying, I have never before felt so seriously the evil of loss of memory and of clearness of in the head. And though I expect to fail someday at the lecture table, maybe like me in a minute, who knows, as I get older, I should not like to fail in ozone on anything about you. Very, very lot of confusion. So, ozone chemical formula was then kind of a topic of research for the chemistry community. Delarive was involved, Jean-Charles de Marignac, both in Geneva. They announced in 1845 that ozone was a form of oxygen, and research went on, but finally Jacques-Louis Sauret, also in Switzerland, determined the density using the Gram laws of diffusion, and he really established that ozone was OOO or O2O, and you can see a little bit of the compte rendu de l'Académie des Sciences, in a building from them, that says, on pourrait par exemple concevoir qu'une molécule d'ozone fut composée de 3 atomes OOO et constitua un bioxyde d'oxygène. Still very good grammatic French at that time. Well, it became, this stopped basically the story of ozone, and Leeds in 1879 summarized all that by saying, by far the most important fact in the long and perspective history of ozone is the recent discovery that there is no ozone. Story concluded. Well, that was in the lab, but now we move to the atmosphere. And here, the French got very much involved, in particular Jean-Auguste Houzeau, who was an agronomist in Rouen, professor in several schools, and he determined by making measurements using a mixture of iodine and arsenic that ozone was a permanent chemical constituent of the atmosphere. That happened in 1858, so it's about 20 years after the discovery of ozone. Now, by the way, Houzeau didn't like the word ozone. He started to question that, and he said we should call it in French oxygène odorant or oxygène naissant, and so he was really pushing for that. So measurements were made since we had this possibility. And you see here on the left, measurements made in the north of Germany between 1875 and 1863, showing basically the annual evolution, seasonal evolution of ozone, but also the diurnal evolution of ozone. And you can see that in the summer, ozone is more abundant during daytime. In the winter, it is the opposite. Now, in Paris, of course, measurements were very much made in different areas of Paris. You see that the second one is Monceau, Parc Monceau, so measurements were made here. The unit, of course, is not the one we know, but it was a unit that was used based on this paper that was making measurements. And of course, they immediately saw sometimes difficulty. So, for example, if you look at Fontaine Molière, they have very low value, but then they say a public urinal is situated almost directly underneath the test. So sometimes measurements can be a bit difficult. Now, systematic measurements were then made in Paris, in Parc Montsouris. Albert Lévy measured ozone between 1877 and 1901. You see here a picture, you never see that very often, picture of the observatory that happened in the south of Paris. Now, very soon ozone was seen as being a compound to be used for water disinfection. Ozone was produced. Siemens had created an instrument to produce ozone. But there was in Paris a Compagnie des Eaux et de l'Ozone, the building is shown here, that the French chemist Marius Paul Otto was putting together, and later on, of course, a number of companies, for example, in the Netherlands or at other places, were producing and selling ozone to disinfect, essentially, water. So that brings us to ozone and human health, because what is interesting, if you go back when the time when ozone and anti-ozone were still on the agenda, medical doctors started to say a few things about it, and they believe that ozone provides a therapy against a number of diseases, and today still people believe that. It was even suggested that it would help curing AIDS. But you can see here, for example, a number of reports that were made at the time. And I'm not going to read all of them. But for example, cholera is coincident with an absence or diminution of ozone, said a few people. And the city of Lyon in France was considered as a city without ozone. They believed that there was no ozone there. And so cholera, they said at that time, Mr. Fournet said, it's more frequent and more severe than elsewhere. So a lot of things were done regarding this, and the slide's not very good, but in particular, a German scientist who got twice the Nobel Prize suggested that the cause of cancer is the lack of oxygen in the cellular level, and he suggested that ozone, kind of inhaled and introduced in your body, would help you to prevent cancer. He got the Nobel Prize in 31 and then again in 44. And if you go today on the web, you will see that this story is still there. What was a true cancer cure lost during World War II? A priceless war relic covered up by our US government for 70 years. The Warburg method for life-saving cancer treatment. And in fact, there are books today still published, Ozone, a new medical drug. You see that there's been this issue of ozone and health for a long time. Now let me move to some other aspect, and in particular, an issue that I think is interesting is how the vertical distribution of ozone was established. Now, again, going to France, Cabane, who was a member of the Academy, and his student Dufay, had noted that Dobson had reported about 300 Dobson units for the integrated concentration of ozone, and then this was incompatible with the low value that were measured at the surface. And so he suggested already in 1920 that probably the maximum in the concentration of the ozone layer was near 50-kilometer altitude. And Guts and Dobson, who made measurement in Arosa, suggested also that the maximum concentration was around 40-50 kilometer altitude. You see here the graph. But then Guts moved further north. He went to Spitzbergen, where he could use, of course, the low or the high elevation of the sun to then provide another height as the maximum. He suggested that it was located probably more like 25-kilometer altitude. But these were deductions, and we had to wait until 1934 when two German scientists, Regener and his son Erich and his son Victor, started launching balloons from Stuttgart, and show you the measurements, basically taking spectra of the ultraviolet radiation as the balloon was moving up, Aufstieg, and then the balloon was coming down, Abstieg, deriving the total amount of ozone above the balloon, and then the vertical distribution. Now, the Americans started to do the same thing, and in fact, the National Geographic Society had a call for frontier research, and people suggested to go in the stratosphere and measure a number of quantities, something like the cosmic rays, ultraviolet solar radiation. And so the first balloon went up from Rapid City in Iowa with 3 men on board, and went up, and unfortunately at 12 kilometers, the balloon, which had hydrogen, exploded. The gondola came down with the 3 men on board. They had parachutes. One jumped, you can see him. Another one tried, but he was a bit overweighted, and with the parachute around, he couldn't make it very easily through the door of the gondola. So the third one went out and pulled the second one out. They all parachuted to safety. A year later, they started the experiment again, Explorer 2, this time They went up to, I think, 22 kilometers. And these are here the first vertical profile of ozone that the three experiments provided, both Regener and the Americans who were making these observations. And you can see that they were different. And so it started to get some controversy. A word about the theory of ozone. And of course, here I don't have to tell you very much. We know that Chapman, of course, came up in 1929 in Paris here at the first ozone conference that was organized, published in 1930, showing that ozone could be explained by 5 reactions, essentially, and highlighting the importance of atomic oxygen in the process. Now, what I found interesting is to read the book. I'm sure you all, I hope you all read it, the book by Charles Fabry, that was written in 1945. I mean, he died in 1945. The book came out in 1950, 5 years after his death. It was completed by Madame Vassy at that time. And let's read a few things here in French, but I'll translate it. Il c'est un peu décevant de constater qu'après 30 ans de recherche, on ne soit pas arrivé à construire une théorie cohérente de l'ozone atmosphérique. So, after 30 years of research, we still don't know how ozone is produced, essentially. No, we don't have a real theory. On a fait une théorie en admettant que l'ultraviolet solaire est le seul jeu comme agent producteur, avec l'ultraviolet moyen comme agent destructeur. Et on s'efforce de croire à l'exactitude de cette théorie, mais en fait on y est réussi mal, et l'on pousse la théorie jusqu'au bout, presque sans croire à son exactitude. So, the theory of ozone produced by UV and this, short UV and destroyed by longer UV is a theory, but clearly Fabry didn't really believe it. Well, 1950, that's the book. 1950 is also the time where Bates and Nicolai discovered that ozone could be destroyed by hydrogen compounds in the mesosphere. 20 years later, Crutzen suggested that ozone was destroyed catalytically by nitrogen oxide, and then Stolarski and Ciceron, Stolarski is here, that's great, suggested that chlorine were also important and could destroy ozone. We'll talk much more about that. So, all these discoveries show that ozone is vulnerable and it's becoming an environmental problem. Now, what is interesting is that already in 1934, Chapman proposed making a temporary hole in the ozone layer for the benefits of astronomers. He used it. And in the 1960s, there was a military interest attacking the ozone layer over rival nations. Let me say a little word on that. Because during the Cold War, there were a number of reports that were published. Harry Wexler, who is the father of the meteorological satellite, wanted to use essentially rockets, and there is a report that's called Modification of the Earth's Upper Atmosphere by Missiles, and he says the subject of weather and climate control is now becoming respectable to talk about. Well, what you find in this report is a summary of some artificial influence of the radiative balance. You can see the last part that says chlorine, and they removed it somehow, but chlorine and bromine, if you put a certain amount in it, so 0.1 and 0.4 million of tons, you could basically produce what they already called in 1961 an ozone hole. And in fact, Wexler was advised by a professor at Caltech called Oliver Wolf how to cut an ozone hole in the a hole in the ozone layer, and the chlorine was that bromine and chlorine might act as a catalyst to destroy ozone. And you see here a little hand note from Wexler who says UV decomposes, and in the presence of halogens like bromine and chlorine, basically you prevent ozone from forming. 100,000 tons of bromine could prevent all ozone north of 65 degrees from forming. So it was really thought that that could be something to be used during the Cold War. But then a few years later came the issue of supersonic aircraft. And basically, it was not completely new in the 70s, because in 63 they were already concerned that the water vapor emitted by the engine could have an impact on the stratosphere. And so Harrison, and I still remember him, he was working for Boeing, and made a calculation that was published in Science in 1970, that a fleet of 500 American SST supersonic air transport could reduce ozone by 3.8% because of the water vapor, essentially. That debate started to become important because Concorde was already flying. Now, an important report is this report published by MIT Press that was on man's impact on the global environment in 1970, and it concluded that no problem should arise from the introduction of carbon dioxide, and that the reduction of ozone due to the interaction by water vapor and other exhaust gases should be insignificant. I mean, gases released by aircraft. And they say in the report, both carbon monoxide and nitrogen oxide can also play a role in stratospheric photochemistry, but these contaminants would be much less significant than the added water and may be neglected. Nevertheless, at the end of the report, you see something that says a feeling of genuine concern has emerged from these conclusions. The projected SST can have a clearly measurable effect in a large region of the world and quite possibly on the global scale. So the problem of the SST appeared, especially in the US, and there were a number of congressional hearings that were organized in 1971, and in particular, James McDonald, who was one of the scientists, I mean, he has been involved very much in trying to look at the presence of UFO, unidentified people coming from other planets, whatever. And so he gave a testimony in front of the US Congress, but he got very much attacked by a Republican senator from Massachusetts, Silvio O. Conte, who tried really to discredit him by saying that, you know, he believed that somebody who believed in little green man was, in his opinion, an uncredible witness. So he was very humiliated by this, and everybody was laughing about him. In fact, he committed suicide in 1971 in the Arizona desert. That has been, I still remember this story when I started my career. But beside the congressional hearing, a very important meeting took place in Boulder, Colorado, in fact at NCAR, 18-19 March 1971, because the US Department of Commerce had created an SST panel to try to address the problem. And you had a number of people at this meeting in Boulder who were supposed to look at the science. And so Will Kellogg was there, James McDonald was there, Harold Johnson, Julius London, Fred Kaufman, and also representative from Boeing. And so there was a big debate. It was a very tense meeting because Julius London came, made a calculation, presenting a calculation, showing that an impact of 500 SST would lead to a 1.2% ozone reduction from water and 1.8% reduction of nitrogen oxide. So relatively small, but Fred Kaufman, who was a kineticist, said, well, what are you using as rate constant? And Harold Johnson said, well, I was looking at your rate constant, and some have been overestimated or underestimated. Your model doesn't work very well. So the Department of Transportation decided to create a program called the Climatic Impact Assessment Program, SIAP, led by Alan Grobecker. There was at the same time a parallel committee in France, led by Edmond Brun from the Academy of Science, and the UK established, I mean the French had the COVOS, and the UK established the COMISA that was chaired by Murgatroyd. And so a report came out showing that the problem could be relatively serious, that essentially the introduction of NOx that you see here on the right-hand side of the upper panel from 500 SST would be larger than the natural production, and so we could expect some relatively large effect, and the first 1D and 2D models were used to estimate how much ozone would be depleted. Now the conclusion came out, and then was still the idea, can the French and British Concorde fly to the US? So another report was written, Concorde Supersonic Transport Aircraft, and you see the value here for Concorde, assuming 12 transatlantic flight a day, and really far away from that number. It was sufficiently low that finally Concorde was allowed to land in the US. Okay, let me say a few quick words about the chlorofluorocarbons. Now, being a Belgian myself, I of course can't resist that CFCs were invented by a Belgian scientist, Frédéric Swartz, who was professor at the University of Ghent. He was a prominent scientist. You see him at the first Council of Chemistry of the International Chemistry Institute of Solvay, which is those famous institute. The CFCs have been done in the academic area, but then were used industrially, and Migle, for example, showed clearly that it was a non-toxic, non-flammable compound. He himself tried to inhale some of the CFC and try with it to, well, he could blow a candle flame, extinguishing the flame rather than blowing apart. Migle was also, by the way, the person who invented the leaded gasoline, and it was then later on that those species were used as refrigerant in refrigerators and in spray can. You see here, all that happened in the 30s, in the 40s. And then, of course, in 71, the first person who detected chlorofluorocarbon in the atmosphere was Rotherford. He had developed an instrument put on one of the ships that was cruising in the Atlantic, and got for the first time this latitudinal variation of CFC11. What is interesting is how the story evolved. There was a meeting in Fort Lauderdale in February 72, and Lester Makta was there, and he reported about Rotherford's measurements. Now, Roland was sitting in the audience, and he took notes, and you see his notes, showing the evolution as a function of latitude from England to Uruguay of some of the chlorinated species. And that led him to think that it could be an important issue. And so, with the students, Mario Molina, University of California, Irvine, they started to work on CFCs and found out that the CFCs were providing the major source of stratospheric chlorine and therefore a major threat for the ozone layer. Now, I'm not going to go much in detail what happened after this, but I'm sure Susan will talk more about it. But of course, I cannot resist to say a few words about the ozone hole. Ozone hole, which was really reported by Farman and his colleagues, Gardiner and Shanklin in 1984. There was also this interesting presentation at a meeting in Greece that Christoph Zerafos, who was there in the back, organized, where Shubachi had a poster and showed himself at the Japanese station, Shiwa, some important decrease. This is now on graphic paper, not on publication. The measurements made by the British team from 1957 to 1984, and you see the decrease in the observation. This is the October one. The British started to ask NASA if they had seen this in their satellite. These are the letters that were sent. You cannot read them, but interestingly, NASA responded, no, we're not doing that anymore. We don't have data. It's not our department. Talk to somewhere else. And so the thing was saved by P.K. Bhartia, was also here, showed basically the first, I think the first satellite view of the ozone hole in 1985, and you see it was still relatively tiny. There were a number of theories to explain it, dynamical theory, solar theory, and maybe some chlorine, but in fact the real explanation came from Susan Solomon, also here, who suggested that chlorine can be activated on polar stratospheric clouds. There was a field campaign organized that proved that out of the three theories that were competing at that time, the chlorine theory and the anthropogenic chemistry theory was the one that was really operating, and in other words, the CFCs were responsible for the ozone hole. Well, all this long adventure, long history has led, of course, to a good time and a very nice time for our community. 3 Nobel Prizes were given in 1995, and it's kind of nice to hear that. But I also think that we have to learn a bit from this ozone theory and see how a field evolves and all the controversial aspect that exists. Today we are 30 years after the Montreal Protocol. So congratulations and happy birthday to the protocol. Thank you.
Thank you very much for this detailed and large panorama, bilingual also presentation. So thank you very much. So now we will give the floor to Susan Solomon, who's going to tell us about the explanation of the ozone hole.
Well, I'm incredibly grateful for the opportunity to be here, and it's a tremendous honor to follow after Peter Sir. You know, I first met Guy in 1980 at one of the ozone symposia. It was, I think, in Boulder at that time. And I was just a graduate student. I was tremendously impressed with not only being able to talk to people like Guy, scientists who were more advanced in their fields than I was at that time, but also really how nice they were. And here we are, many decades later, still friends and colleagues. It's been tremendous. So I want to apologize in advance. You'll see me standing up every now and then. Those 37 years have also brought me some back problems, which I'm dealing with right now. So it's not that I'm bored, it's just that I have to stand up from time to time. So the first part of this talk, I'm going to briefly review the discovery and explanation of the Antarctic ozone hole. I'll skip quickly over the bits that Guy covered. And then in the second part, I'll talk about what I think can be described reasonably as mounting evidence that the ozone hole is actually beginning to heal. The Paleozoic period of the 1970s was an exciting time, as Guy has already described. At that time, we thought that the chemistry of the stratosphere was entirely gas phase. The only thing that would matter would be gas phase chemistry. And he's described the catalytic cycle that Stolarski and Cicerone discovered, and then the subsequent work by Molina and Rowland, which won them the Nobel Prize along with Paul Crutzen for showing that the chlorofluorocarbons could be significant in this. And their key point was really to emphasize the fact that these compounds are chemically inert, that they live in the atmosphere for some 50 to 150 years, and basically everything, almost everything that had been emitted up to that point was still in the atmosphere, which was really quite shocking because normally people thought of things as reacting quickly and being cleansed, and that clearly wasn't happening with these very, very special molecules. Another thing that this figure shows you is that you can actually get a Nobel Prize even if you don't read your page proofs very carefully and you type it out for errors. This is actually how it was published. But anyway, it was a great paper and a very, very important paper. At the time, we thought that if we kept using chlorofluorocarbons at the rates we were using them in the early 1980s, I should say, we thought that the CFCs and the halides, which contain bromine, might deplete the ozone layer someday. We thought maybe 5 to 10% depletion could happen in something like 100 years. Those were the sort of numbers we were dealing with in, say, 1983. So it was a small effect. It was far in the future. Sounds a little bit like some other problem that we really worry about today, but we won't talk about that. Because in the United States, we don't talk about that problem anymore, right? Just kidding. But in 1985, everything changed. We weren't talking about 5 to 10% in a century. We were talking about literally half of the ozone layer being gone at that time. And in a place where we never expected it to happen. No one predicted that Antarctica would be special. So the measurements that really sparked all of this off are that little graph over here in the, I hope I can do this, yeah, in this corner, that the British Antarctic Survey published. That's what they had when they published their paper. If you look at what the record has evolved to, that's what it looks like. I didn't add this last one, but it's almost up to date. These are the October monthly averages. Please remember that. I'm going to come back to it later. October was the month for the ozone layer discovery. We'll talk about that in a few minutes. The Japanese measurements at Showa were a wonderful confirmation, and of course the US measurements at the South Pole, those measurements came later, as did the satellite pictures that are so beautiful that underlay this graph, and I'm sure PK will tell us a lot more about those. It was a huge challenge to science. How could this be happening? We didn't think it would be this big. We didn't think it would happen now. We didn't think it would happen in Antarctica. And it was a tremendously exciting time to be involved in the explanation over the first few years, the late 1980s and early 90s. There were later studies, and particularly the question began to arise, which I'll deal with in the second part of this talk. What about the recovery of the ozone layer? What's that going to look like? And in, I think it was the 2012 assessment maybe, we talked about 3 different eras. First of all, you can see the rate of decline of ozone slowing down. So as the ozone dropped so fast in the early, say, the early 80s to mid 80s, then it slowed down. Then it became flat. So from a sort of picking up on the recovery analogy, you could say this would be the period of remission for the ozone layer. And then you would actually begin to see some sort of improvement. And you could attribute that improvement to the halogen decreases. And we'll call that the healing period. I think that's a nice word that's helpful from the medical analogy once again. So this is that, actually that same letter that Guy put up. It's the whole thing, so you can really see it. And it's from Jonathan Shanklin of British Antarctic Survey to somebody at NASA Wallops. And I think PK will talk about the fact that part of the problem is this wasn't sent to the right NASA. It should have gone to Goddard and it went to Wallops instead. But one of the things that's exciting about this letter, and very prescient actually, of Farman and Shanklin and Gardner, was that they said, you know, our values are really low in Antarctica, and we just don't think this is normal. Could it be connected to the El Chichon eruption? They actually mentioned volcanic connections being possible, and I'll talk about that quite a bit later, but it was a very forward-looking thing that they thought about. So I was, at this time, a young scientist now, mid-1980s. I was, 29 years old when the British Antarctic Survey paper came out. You can do that math. And it was incredibly interesting to me. I was lucky enough actually to get the paper to review through an indirect means that I won't go into. But I was the official reviewer, and one of the two, I don't know who the other one was. And interestingly enough, in those days, you would do things like try to help the colleague along, and so I sent them this figure, this part of my review, which I drew by hand on graph paper, yes, just like Guy was showing. And what it is the average of ozone data that was available from Showa, from the Japanese station at 69 South. So I had been to a meeting in Japan a few years earlier, and I heard a little presentation about the Showa data set, and I thought, gee, somebody should go back and just take a look at that data. So at the point where I was reviewing the paper, all I did was average all of it, and this is what the ozone profile looked like, with a maximum at about 18 kilometers. These are all September measurements. And I pointed out to them that, hey, more than half of the total ozone is below 22 kilometers. So, I said, I don't think that this could be gas phase chemistry, because gas phase chemistry can only work higher up. It's not going to do anything down there. And the paper inspired me, actually, to go on and do the work that I did with Rolando Garcia, Sherry Rowland, and Don Wubbels, the 86 paper in Nature, where we said, well, look at where it's missing. And that was, in my opinion, one of the most important contributions to this paper that we could have made. So there again is that same profile that I sent to Farman and Company, but I added on the data for 1982, which I actually didn't have, I don't think, at the time that I wrote to Farman. It came a little later. And you can see that there's this huge region where there's like nothing there. It's depleted by 50%. I mean, there's still some, but it's quite depleted. And there's, interestingly enough, no ozone depletion up around this altitude, which would be about 30 kilometers. So most of what was missing was between about 10 and 25 kilometers. That just could not happen from gas phase chemistry. I tried very hard to make the model that Melanda Garcia and I built produce that kind of an ozone loss, and I just couldn't do it from any gas phase mechanism. I tried all kinds of things actually back in those days. I had a lot of fun with it. There was a paper that suggested that the ozone hole might be caused by NOx, reactive nitrogen coming down from above, caused by auroral activity or something like that. And that clearly couldn't explain it because nothing was happening at 30 kilometers. It couldn't, you're going to get a big depletion down below, you better have an even bigger one up above, and that was not happening. So there was this very important fingerprint in altitude. The ozone was missing from 10 to 25 kilometers, not 40. And so we suggested that reactions on the surfaces of polar stratospheric clouds might actually activate the chlorine in a way people hadn't thought about that could produce this sort of chemistry. And the key reaction that we proposed is an important one, HCl plus chlorine nitrate. There's also been some talk about HCl plus HOCl, which can also contribute at some times of year. That Robbie, in fact, actually discovered that reaction, if I'm not mistaken. The way that this works is you take two compounds that aren't reactive themselves towards ozone, and you react them on the surfaces of these clouds. So those are reservoir compounds. And you make something that then becomes very active. So you've activated the chlorine for much more ozone loss. Sunlight's also involved, making atomic chlorine, which goes on to make CLO, and then that's been activated for ozone loss. And you can shift the chemistry. You can shift it from a regime dominated by gas phase chemistry that can only destroy a little bit of the total column because there isn't much ozone up at 40 kilometers, down to the regime where most of the ozone sits, the heart of the ozone layer, and that's how you get these 50 or 100% depletions. Nowadays, we routinely see ozone going essentially to zero in the heart of the ozone hole. So it's been an incredible shift in how the chemistry works. I was also very, very fortunate to have the chance to go to Antarctica myself to make measurements of chlorine dioxide through visible spectroscopy. And that's a picture of me arriving in Antarctica in August 1986. It's noontime, but it's quite dark because the sun isn't getting above the horizon. It's the most beautiful place that I've ever seen in my life, and it was truly the opportunity of a scientific lifetime. I was actually at that time 30 years old, so really amazing. One of the key people who worked in Antarctica with me was Bob DeZafra, and he and his colleague Phil Solomon did microwave sounding, vertical sounding of chlorine dioxide and chlorine monoxide, excuse me, while I was measuring chlorine dioxide. There was also, I'd be remiss if I didn't mention the aircraft campaign, which I think Mike Carrillo will talk about in a few minutes, and those measurements also were absolutely key, measuring chlorine monoxide by airborne resonance fluorescence on board the ER2, and really those were the key measurements. So if you put those together, which I think is a nice thing to do, you can actually stack the McMurdo ground-based measurements from DeZafra and Company on top of the aircraft measurements and come up with the altitude profile of CLO in Antarctica in September of 1987. Gas phase chemistry would predict almost no CLO, but instead it's enhanced by this factor of 100 up to something like a part per billion, so 1,000 parts per trillion from a normal value of like 10. And at those kind of levels, you can get 2 to 3% destruction of ozone every day using the chemistry that actually Mario Molina and colleagues established, the CLO dimer chemistry, which I won't have time to talk about in detail, but they were the ones who identified the key catalytic cycle. So at that rate, all the ozone is gone in about 5 weeks, and that's how you get ozone driven to zero in the heart of the ozone hole. You've got to have CLO on the order of a part per billion. This was an incredibly important fingerprint now in altitude, where you could show that the enhanced CLO was exactly at the same height where the ozone was missing, from about 12 to 24, right where the polar stratospheric clouds are. And of course, the aircraft campaign could also not only do some vertical profiling, as I just showed you, but actually fly along as a function of latitude and do these beautiful, and really these were the measurements that were the ones you could talk about to the public and to policy people that were really convincing, showing that where the CLO increased as you flew into the ozone hole, that's exactly where the ozone dropped. It was really tremendous. Nowadays, we also have these bird's eye fingerprints from space by people like Waters, Santini and colleagues, just showing you a couple of years of CLO and ozone data. You can't really tell the years apart. Lots of years are really, really cold in Antarctica, which gives you massive ozone loss. There is some variability from year to year, which I'll mention in a minute. Why do we have an ozone hole in the Arctic? Very simple, it is warmer. Antarctica really is the coldest place on Earth, so we don't have clouds typically as late in the season as we do in Antarctica, and therefore we don't have that magical combination of cold temperatures and sunlight that you need. Lots of nice work has been done on the types of polar stratospheric clouds and why they affect the chemistry. We originally were really all thinking, I think, about water ice clouds, and then there was beautiful work on nitric acid trihydrate clouds by people like Paul Crutzen, Brian Toon, Frank Arnold, actually. The bottom line today is complicated, to say the least, actually, but the idea is that liquid sulfuric acid aerosols form because we have sulfur in the stratosphere. Actually, Paul Crutzen's the one who first thought about that, I think. They can cool down. You would have thought maybe they would freeze, but they can actually supercool. They can become the seeds for PSC1s, which are the solid particles, the NAT, nitric acid trihydrate, and then ice particles. But actually, you can, and those would be PSC2s, I should say. But you can also form supercooled liquid particles, and both our types of particles are important. Lots of people have contributed to understanding the microphysics of these particles and how they form, how they transform. I've given it not nearly enough time here, and I won't have time to go into more detail, but I just want to mention the work of Maggie Tolbert, Mario Molina, Ravi, Toon, Karsla. I've already mentioned some of these people. Thomas Peter, Tabazadeh, and Koop, and actually many others. This has been a tremendous area of work. And the main thing that is important to remember is it's beautiful to think about all those different kinds of polar stratospheric clouds, but actually, really, they don't matter that much what they are. I mean, they matter, but what kind of particle they are doesn't matter as much as you might think, because they're all capable of becoming very reactive and making an ozone hole if the temperatures drop below 192 Kelvin. It has to be cold. 195 won't do it. Some papers have suggested that. I think it's clear that that's not true. We've shown that in a paper in JGR in 2015. You really have to get colder than 192. And the reason is that you have to get cold enough that you can get enough liquid on the surface and you can get enough HCl into the surface, so that then when chlorine nitrate or HOCl hit the surface, you can get reactions that deplete the HCl and convert the reservoir into the active species, as I've already mentioned. So, you know, the liquids will do this, so will the nitric acid trihydrates, it seems, although there's some debate about the kinetics there. And certainly the water ice clouds will do it, because there's a quasi-liquid layer on water ice that's really quite important. So there's significant remaining uncertainties in the kinetics, actually, but they're details at this point in a sense. There are very few kineticists, so I'm not sure when we'll ever resolve it, if we will. Basically, we've observed so many of the important chemicals and seen their fingerprints on this problem that there's, and by the way, it's important too that these were independent measurements by different methods. So you had measurements of HCl, NO2, NO, CLO, OCLO. They all showed the same story. There are massive perturbations to Antarctic chlorine chemistry that happen on polar stratospheric clouds when it gets below 192. That's what depletes the ozone layer and produces an ozone hole. It was amazing to be part of the process whereby, in the space of literally about 2 years, you know, between 1985 and 1987, the science community got together and answered this very important question for the world. That was incredible that we could do it that fast. And it's a testimony to the very, very great experimentalists that we have in this field. And I'm not one. I use some instruments, but I didn't build them. Is the Montreal Protocol working? We can obviously say yes, it's working, and the easiest way to do that is look at CFC-12 concentrations and look at how they've increased and how they're now dropping off. So they're dropping off slowly because this molecule has a lifetime of more than 100 years, so it's not going to be gone very quickly. There'll be many decades before the ozone hole will fully recover, but it might be starting to heal, and I'm going to talk about that in just a couple minutes. So the full recovery of the ozone hole will be late compared to other latitudes. I want to acknowledge the work that Paul Newman and his colleagues have done on this. There's a lot to that story. I'm just going to say it's going to be late because Antarctic air is both cold and old. It's not only cold, but it's also old. And that actually means that the recovery will be sometime in the latter part of this century, and probably the global ozone layer will recover faster. We've really owe a lot to the policy community. I wish I had time to talk about all that, just to say here that the original Montreal Protocol would have allowed the amount of chlorine in the stratosphere to continue to increase because it was a freeze on emissions at then current rates. So keep putting stuff in, it's still going to build up because the lifetimes are so long. I'm sorry, this one is Montreal. This is no protocol. London was where the developed countries agreed to phase out immediately, then Copenhagen, then Beijing. So at meeting after meeting, decisions were made involving what to do that had inputs from the international scientific assessments. And many people in this room have given big chunks of their lives to making these assessments be successful and useful. John Pyle, of course, Paul Newman now, Gabe Fahey, Ravi. But before that, I just want to emphasize two people whose names haven't been mentioned yet, Bob Watson and Dan Elbert, of course, who were the leaders for many years. And and I should mention Gerard Gervais also. So lots of people, I haven't mentioned them all, but I'm going to have to move on quickly here. I think the key thing that Albritton brought to this was a clear thinking about dividing stuff up, and in particular for the issue of this problem. We've gone through credibility in just a few years. Do we understand the problem? Yes. Are we credible? Manageability, what can we do about it? And now we're really into the accountability phase, which is important. And I don't think we can let the people who fund our research get off too lightly here. I mean, yes, we've already done things to manage these molecules, but have we shown that they're going to be effective? And that we're still in the process of doing that, so we really need to keep going. The people in the climate science community do attribution of global climate change, and I'm now going to talk about attributing the healing of the ozone hole for just a couple of minutes. They do that really carefully. They look at observations of global temperature change like this, and they say, well, what would happen if all you had were natural forcings? And that's the kind of simulation they get. And then they say, okay, well, what happens when we add natural and human effects? And they do very, very detailed statistical matching of what the model can do and what the observations look like as a function of latitude and actually sometimes even as a function of height. And that's what allows them to go through this very meticulous phase of going from saying, well, the balance of evidence suggests a discernible human influence on climate. I'm sure you're all familiar with that statement that IPCC made in 1995. That's kind of similar to our early statements about ozone. We think we can say that that chlorine's influencing the ozone hole to some extent, And then they became progressively more and more quantitative, and I don't have room to put the most current one on here. So, but very likely someday soon it will be virtually certain. It moves over time as more information is collected. So as we move into our accountability phase, I think we have to get quantitative on this. We can't just wave our hands and say, oh, we see a trend. That's what we've been doing for a while. We have to be much more quantitative. It's not just simple trend statistics. You have to account for confounding factors, such as Pinatubo was for climate change. And they did that statistically. So in the next part of the talk, I'm going to talk a little about data, models with and without including volcanic influences, and what dynamics and temperature do to what we're trying to see when we look for ozone healing, when we look at this important early stage of recovery. So I'll be showing you data, and I'll also show you some results from WACM, from the whole atmospheric community climate model, constrained by observation, so using mirror reanalysis for temperatures and circulation, and also from free-running WACM, where it generates its own circulation and temperatures. So here's the ones from the constrained dynamics and temperature. You've seen this in our science paper that came out in 2016. And the figure that I'm showing you here is the October values. The black line is the SPUV data for the polar cap. The purple line is the South Pole. And you can't really see them too well because they lie right under the observed data is actually the model. When the model is constrained by reanalysis, where the temperatures and circulation are what's been derived from observations, it does incredibly well. So the red line is the model with all singing, all dancing, as some people would say. So it's got not only the chemistry and dynamics in there, it's also got volcanic effects, and I'll talk about those in just a second. If you only put in chemistry, so you basically freeze the dynamics in 1999, and you just let the chemistry go, you get this very slight recovery, but it's pretty small. And in October, the ozone is highly variable. If you look at September, you see something a little bit different. You see recovery, which is statistically significant, and you see that the model does, again, a remarkable job at reproducing every single up and down here. So you really shouldn't, I think the key point that I want to make here is there is no mystery about the ups and downs. We can model them very well, and we know what causes them. That means that we ought to be viewing this, the ups and downs, not as just random noise. And when we do our statistics, we shouldn't say, well, that's just noise. That would be silly. You have to include that when you evaluate uncertainty in a problem like this. So you can take that out, and you can then say something, I think, even more quantitative about the healing. Now, the other thing that's important here is that the variability is a lot less in September than it is in October. That's one reason why you might want to think about looking for recovery in September rather than October. It's just less dynamically active, and I'll talk about that in a second. So the other thing you can do is look at profiles of Antarctic ozone loss or recovery. And so this is over the polar cap from the model, and it's showing you comparisons to the Showa data and the South Pole data. So those are the dotted line over here is Showa, actually, so that's the depletion era. And here's the healing era from Showa and the South Pole. And you can see how, again, the profile exactly matches what the model suggests it should look like. It's absolutely a remarkable fit in altitude. Again, a key fingerprint for this problem. Chemistry alone would get you halfway there. You get the rest of the way according to this model from what the dynamics and temperature are doing. But remember, one thing to bear in mind, so here's the depletion era, here's the healing era, and chemistry is half of it, the rest of it is dynamics and temperature. But within uncertainties, 100% of it could be chemical. Of course, more of it could be dynamical, but it can't be zero. Actually, dynamics cannot drive this all the way to zero. And part of the reason for that is you've got to think about the role of ozone temperature feedback. When there's more ozone, it will be warmer. We know very well that the ozone depletion has cooled the stratosphere. I'm going to show you that in just a second. So when ozone increases, it actually warms, and that will mean that there'll be less depletion. So that's a feedback, but it isn't included when you use the fixed dynamics version of WACM. It is included in free-running WACM. I'll show you that in a second, too. But when you're using the observed temperatures, you're assigning any influence of temperature to the dynamics temperature column. You're not allowing for the idea that chemistry could actually help the temperatures warm. So that's an underestimate, and I'll get back to that. Okay. literature saying, hey, these ozone pools are observed that maybe it's due to chlorine when chlorine is being taken care of. Well, the reason, of course, I think, as you know, is that there's been a volcanic contribution. So the difference between this year that year and having a record year is actually it's what you can see that actually it's hard to see, but this line showing you what would happen in the volcanic clean case pushed up the extra 5 million years. The record is the volcanic effect according to this. Our significant volcanic effects in other 2011 was much year, and I'll show you that too. So, the seasonal evolution of the size of holes. Here's how the ozone hole grows, where it's defined as the area where ozone is less than 220,000 units from the satellite data. You can see how it grows as a function of day to year. This is an area over years 99. Data. Take from here. Very interesting differences that starts later. Why is it just we have actually that true case. It's also true for the 2015 case. And I think it's worth to say that the same, but you do think it's prolong it and make it even bigger. So that's what I'm really arguing about, the timing of what volcanoes do. They don't actually do much in the early period, and I don't have time to talk about all the chemical reasons for that. If anybody wants to know about it, they're welcome to ask me. But whether you have a volcano or not doesn't actually affect things too much in the early part of the season when it's first happening. And maybe I do have enough time to, well, I think I'll skip saying why. So in the data, you can look at things like this. So what I'm plotting here is the day when the ozone hole gets bigger than 12 million square kilometers. So it's kind of halfway to its maximum. It's going to get to about 2025, so 12 million is roughly halfway there. What day does it get there? And it needs to stay above for more than 3 days. So you don't want to be too influenced by the little jigs and jags. You want to really get the mean value. And so in the old days when it was first opening up, you had to wait till mid-September to get that big of an ozone hole. And then it got earlier and earlier and earlier. And now it's getting later and later and later, even in the cold years. That was a key point of the science paper. And to me, it's the most compelling part, really, of the whole attribution story on this. Because we understand that chemistry. And it has to do with the fact that by the time you get to October, you've run out of ozone. If you've driven ozone to zero, or almost zero, you can't make it any lower than that. Whereas the rate at which the ozone gets lost as the hole first opens up is very sensitive to the amount of chlorine that you have. So that's really what's going on here. Okay. This isn't really something that we thought of first. I have to say that there's a really nice old paper that by Hoppe et al. And JGR, I think Richard Bevelak was part of this paper too, where they were looking at things that were happening in the PROM data. And they noticed that whether they had more or less chlorine, the ozone hole would open earlier or later. That's the difference between the green and the red lines on this graph. So I think I'll not say any more about that. I'm just going to show you, this is just a little box model calculation that I did to make it really simple. So if you have the maximum, if you have a lot of CLY, you drive the ozone to zero very fast. If you have a little less CLY, it happens slower. Same thing with a lot less. And so you have no effect on the October monthly average because it's almost zero in all cases, but a big effect on September, and that's why September is so key to this, even though I think we were all sort of brainwashed. Because the British Antarctic Survey discovered the ozone hole using October data, we thought that would be the time to look. That's not the time to look. September is the time to look for the reasons I just described. Okay, so let's take a look at the Kelbuco eruption in a little bit more detail. I showed you stuff from a model calculation we have done on Kelbuco. We now have a paper that's been submitted to JGR. I'll be happy to send anybody copies of it if you're interested. That shows how our model results for the Kelbuco aerosols actually compare to the Callio. Evolution of the optical depth, I think it is, or maybe it's extinction, as a function of latitude and month at 100 millibars, so you can actually see the Kelbuco aerosol. It means that the subpolar region, just at the edge of the ozone hole, is just flooded with all this extra aerosol. And it happened because of the timing of the eruption. It got there at just the right time. You can see it getting there in late August and September. This is just the same thing as a slice. This is the amount from Calliope as a function of altitude and latitude. Here's the same thing in the model. We are avoiding getting into the issue of did it affect PSCs in the vortex in this paper, because I think it's very hard to say whether or not that really happened, either from data or from the model. I don't have time to talk about that in depth, but Calliope, I think it's tough for it to tell the difference between what the PSCs are doing through temperature variability and what might be caused by volcanic enhancements. But outside the polar region, outside the vortex itself, actually it's subpolar and on the edge, it's not very difficult to use this data as I've shown you. So I think it's pretty cool to be able to do that kind of modeling, and I'm happy that I was able to work with, actually Anja Schmidt was keen in being able to do this, along with Mike Mills and Kinnison. So, lots of people have worked on how the ozone hole cools the Antarctic stratosphere. I just want to say a couple of words about that. Because there's so much less ozone, you just don't have the ozone there to heat the air when the sun comes back, and that leads to tremendous cooling. So Randall published this nice paper showing it at all these stations. And I think an important question to ask is, do we see a mirror image in warming now? Not just a mirror image in ozone, but a mirror image in warming. And so that's what I'm showing you here, where the top is the temperature trends from as a function of pressure and month. And this is from Mira on the left. Same thing from Mira from 2000 to 2014. I should have said, over here is the depletion era on the left side. On the right side is the healing era. The top is reanalysis. The bottom is the free-running WACM now. So being allowed to compute its own temperatures. It's an amazing match. I could spend an entire talk just talking about the things that match and the things that don't match in this figure. And I really urge you to take a look at the paper. It's in press in JGR, and I think of it as the mirror paper now. And that's really the key point, that there's this, sorry about that, there's this remarkable mirroring of the temperature changes. You see cooling in the lower stratosphere in the depletion era. Now you see warming in the lower stratosphere. That's true in the data, it's true in the model. There's a pretty good match in the lower stratosphere. Other things are actually happening in the upper stratosphere. As I say, I'm not going to have time to talk about those, but maybe you can ask some questions. I'd be happy to try to answer them. But, the cooling was on the order of 6 degrees. The warming's already on the order of a few degrees. If you take the ozone changes that the free-running model produces, and you ask the question of a radiative code, how much temperature change would that ozone change have produced? You get stuff that looks like this, where the bottom is from chemistry alone. So just like what I showed you before, fixed 1999 temperatures and dynamics, calculate what happens as you get to the present day. Chemistry alone would give you about 2 degrees of warming in the lowermost stratosphere, which is a good chunk of what's actually been observed. Not all of it, probably. If you also include what the dynamics and temperature trends mean for the ozone trends, you get even more warming, and in fact probably too much warming, which tells you that there's been some kind of dynamical cooling going on recently, which is really interesting. I think there's a tremendous number of questions that surround the whole ozone temperature feedback effect that the community really has never answered. We've never answered the question, even if you go back here, how much did the cooling trends actually contribute to the ozone loss? We've never answered that question. If it's colder, there'll be more polar stratospheric clouds, of course. How much more ozone loss does that imply? We all know it's true, but I can't think of a good paper that really quantifies that in detail. So, and it's certainly contributing now in the healing era, as we show in this new paper. So, the ozone temperature feedback has been an important assist to the healing. You can't just do, I just want to emphasize, you cannot just do linear regression. That's what this means. I mean, you can do it, but it's important to understand that there are interactions between the terms. It's important when you try to do linear regression to take out aerosols that you can't do that very easily, because it's not just how much aerosol you have, it's how cold it is. Volcanoes don't do anything in a warm year. They do a lot in a cold year. It's a non-linear interaction between aerosols and temperature that actually matters for this problem. So there are challenges in doing any kind of regression study. We have to be a little more sophisticated, I think, in how we do it. I don't have all the answers. I hasten to say, I think this is an important research question that we are all thinking about now and working on. It's exciting, it's interesting, it's every bit as important to do the accountability phase as it was to do the credibility phase, with a lot more sophistication than just saying, oh, I do my trend, I see an error, I see random noise. The year-to-year variations in dynamics are not random, nor are they well taken out by simple indices. And the year-to-year variations in aerosols are not well taken out by simple indices. So it's a tough, tough problem, and we're all having a lot of fun working on it. We shouldn't be intimidated by it. We should just be excited by it. And I want to close by thanking you for your attention, and also thank many people in this room for many things. I've been very, very blessed to know and work with many people here and in other parts of the world. Being part of the community that has dedicated its life to addressing the science of this problem and to doing assessment in the way that we've done it, I think we can really all be very, very proud. It's a pleasure to reflect on it here. Thank you.
Thank you, students, for this very pedagogical and inspiring talk. Are there questions?
It's all pretty clear.
Yeah, everything is clear. Okay, thank you. Maybe they have questions in the discussion later. So now we will have the presentation from P.K. Bhatia about the discovery of the ozone hole.
Okay, in my talk, I'm going to focus primarily on months before and after the publication of Joe Farmer's paper, and you're going to hear a lot more about the later satellite data from a lot of other people, but I'm just going to focus the 1984-1985 time period, where I was very much involved in. You're going to see a lot of ozone hole pictures. This is my favorite picture, where the ozone hole split into two in 2002. And people are worried about that maybe one part of the ozone hole might move up in north and maybe destroy life. So this has been a real problem. A lot of people have been very much concerned about what is happening with the ozone hole and what impact it may have on the life. I want to start with this book that was published several years ago. And the book talks about the impact of highly improbable. And he talks about the fact that in many different fields, things happen with far more greater frequency than people believe about improbable event. And this person, Nassim Taleb, called that a black swan event. Black swans do happen in the nature, but they're very rare. And so he said that a black swan event is an event that is statistically improbable. You cannot really even measure the statistical probability of that happening. It had no prior warning, and it has a major effect in the field in which it happened. And if you think about it, the Antarctic ozone hole fits this definition very well. As was pointed out, at that time, we were thinking about 1% per decade type ozone changes, and the changes turned out to be much, much larger than that at a much shorter time period. So it was definitely statistically improbable. It was a total surprise. I don't think that there was any kind of previous warning that something like that is going to happen. And it changed the course of a multi-billion-dollar industry. Now, you may argue whether or not the Montreal Protocol would have happened or not without the discovery of those on hold, but there is no question about it that the public policymakers and the public were greatly influenced by what was happening over Antarctica. So it had a huge impact on the public's perception of what was happening in the ozone layer. You're going to see many times mentioned this famous paper by Joe Farman and colleagues. And I'm not going to go into a lot of details about it, except to say that to me, when I was looking at this data, or my colleagues were looking at the data at that time period from satellite, the thing that was puzzling to me, puzzling to us, was you see on the right panel here is the seasonal dependence of the depletion. We just couldn't understand how chlorine in the atmosphere can produce something that varies so much between spring and the summer, spring and the autumn. And the question was, why was the depletion so much larger? And this paper, they first talk about the effect of temperature being the cause of it. Now, of course, the chemical mechanism was not very well understood at the time, but what was certainly understood was, they talk about is the effect of the temperature, which turned out to be correct. So this paper was published in May 1985, and soon after that, there was a meeting in Prague, Czechoslovakia, Yakayama meeting, and that held in August 1985. And this is the first time that I actually presented the image of the Antarctic ozone hole. And this was made in a very early graphic system, very poorly, in a poor version of the present graphic system, very, very expensive at the time, $100,000 something, the machine that was used to create it. But it basically talked about this little red thing in the middle that we found it very intriguing. But of course, at that time, we had no idea that this was caused by chlorine. We didn't really understand the mechanism of that. So all we were talking about is observation of the anomalously, the title says observation of anomalously small ozone densities in South Polar stratosphere between October 1983 and 84. But of course the Farman paper had come out by that time, and it created a lot of interest in the community. Actually, the full paper, I had a full view graph which showed here the 1979 and 1983 picture. And it's very clear that whatever happening was there was very sudden. 1979, we didn't really see anything at all. In 1983, it suddenly appeared. I also want to show, there were other images that I showed at the time, and that was on Nimbus 7 SBUV, which is another instrument on the same satellite. And this one very clearly shows that the changes were very different in the September-October time period, where the increase, the change was very large between 1979 and 1983 in the September-October time period, but not in other time periods. There was also some profile data that we showed at that meeting. Unfortunately, the SPUV instrument that was used to make this plot doesn't have high enough vertical resolution to really capture the full extent of the ozone hole, but it did show that most of the decrease was happening at a much lower stratosphere. Now, right after this meeting, there was a meeting in Salzburg, Austria, which was organized by the principal investigator of SPUV instrument, Donald Heath, who's right in front of here. And Sherry Rowland was here, he's in here. Bob Watson was there, and there were several other people who you might recognize in this picture there. And Sherry Rowland at that time asked Don Heath to take the copy of the presentation I had given, and he then gave it to New York Times, where it was published in November 7, 1985. And that is how this phenomenon got brought into the attention of the common public. And of course, it created a huge amount of interest. And all of you know that there were a lot of publications at the time that showed these images in various different forms. So it was really had, and of course, any place you go to, any place person you talk to, and they realize they're working for NASA and working in the ozone field, everybody was interested in finding out what exactly was going on with ozone hole. So it really definitely did capture the attention of the public. So I was thinking about it, why did it has such a big influence? And I had the pleasure earlier this year to be in the solar eclipse that happened in Idaho, over the US, and I was in Idaho where this picture was taken, and the amount of interest the solar eclipse produces among the people, and that people are still very afraid of it, even though we know very well how this happens, and it is not really a phenomenon, but all over the world, people talking about hurricanes perhaps being produced by the solar eclipse and so on. So I think the ozone hole in the same way captures the imagination of the people. It's like a hole in the ozone or an eclipse of the ozone. And I think it has a similar kind of fear, concern it generates that eclipse has done over the centuries among people, even though a lot of people don't understand what exactly is the cause of that. Okay, so this is basically a very brief history of what, of the ozone hole discovery at the time, and I'm sure we're going to hear more about that. But I'm going to take a few more minutes that I have and talk about this controversy that I think was alluded by both Susan and Guy about why did NASA miss or did not come up with these results quickly enough. And so this is the question that people have asked, is why did NASA miss the discovery of the ozone hole? And this has been published in many different forms, and this is one example of it from a very respected scientist in atmospheric chemistry and physics textbook. It talks about the fact that after the publication from our paper, it turned out, after inspection of the satellite data, that low ozone concentrations were indeed observed, but were being systematically rejected in the database as being outside the reasonable range of data. So the question is, what exactly happened? And I'm just going to talk about that for the few minutes about what exactly happened. So to do that, I need to take you back 50 years from now. So we're also celebrating another anniversary, which is the first time an algorithm was published, exactly 50 years ago, March 1967, from two scientists at NCAR, J.B. Dave and Carl Metier, who said a preliminary study on the possibility of estimating total ozone from satellite measurements. So this was the first paper where they say it's even possible to make measurements of total column ozone from satellite. And this was really a match made in heaven, because J.B. Dave was trained at UCLA, and they were using modern computers to start modeling the radiation in the atmosphere, and he developed some of the advanced code at the time with polarization and everything included to estimate the top of the atmosphere radiation in the UV, which was very difficult to calculate because you have to account for the Stokes vector and things like that. And Carl Metier, many of you know, he was the president of the Ozone Commission, and before that he had worked with Hans Deutsch about on the UMKET algorithm, and so he was a pioneer in remote sensing techniques. And he understood the strength and the limitations of the remote sensing technique long before other people did. And one of the things he knew at that time is that in order to convert a remote sensing data, which is not very similar to other kinds of measurements one makes, you have to have prior information. So the role of the prior information was very critical in trying to interpret remote sensing data. So in their first paper they have, they actually had a set of profiles that they used, they call it standard profiles. There were 6 of them, which were constructed from ozone sound that are available at the time. I'm not sure how they, I think they may have added UMKET data at the top level. So this was a key part of the algorithm that they had published in about 50 years ago. And only 4 years later, Carl Metier wrote this paper where Nimbus 4 BUV was launched in April 1970. And this paper was the first time somebody had taken the data from satellite and produced total ozone from it. And they had comparisons with Dobson and showing that the agreement is extremely good with the 95% correlation between satellite measurement and the ground-based measurement. So in that paper, they had actually extended these standard profiles to 16 because these profiles were really, really critical for getting highly accurate ozone values there. And these values were different for different total ozone amounts, different latitude bands. So they knew from ozone sound observations how the ozone profile varied. The peak of the ozone density changed from 25 kilometers in the tropics to much lower in the higher latitudes, and also changed with the total ozone amount itself. And all of that information was put in there in this particular work that they had done. And trying to improve this profile and putting it in the algorithm has been one of the primary activities since then. So as more and more data has been collected from the satellite and the ground-based, particularly ground-based data, and also the satellite data, we have been adding more and more information to these standard profiles. And in fact, more recently, it has gone up to 1,500. The algorithm that is working right now in Belgium, BIRA, they are using 1,500 profiles also to interpret the CEO's data from the ground. So these profiles are really, really critical. The problem was in 1984, when you're looking at the data, the range of total ozone values under which we operated was 225 to 525. In other words, the ground-based data basically limited us to retrievals because there were no significant amount of data available for ozone less than 225 or ozone greater than 525. And so to go outside that table or outside the range of those values, we had to extrapolate. So that's what we started doing when we found out that the ozone values are going very low. And the problem was when you do that, you get very nervous about you're really going outside the range where your prior information is available, and that starts to make you very nervous. So we had to find some ground-based measurements to try to validate that what we were getting at that time was really correct. And so the only measurement we could find at the time was from the South Pole Station over Antarctica. And that station had been very reliable in the past. In fact, there was a paper I published in 1984 showing a comparison between the satellite data and the ground-based measurement. That was remarkably good. It's maybe hard to see, but the Dawson data are shown in plus, and the Towns measurements are shown in the solid lines. And the agreement was extremely good. The problem was when we got the 1983 data from Toronto, where the data were archived, we were measuring 170 Dawson unit, and the ground-based was reporting 350 Dawson unit. It's not clear what happened then. The later the data were retracted, you really can't get the data anymore. Some measurement error was made. So the problem was when you have that kind of a difference between the satellite and the ground-based measurement, there's no way you're going to publish it, or you know way you're going to report that kind of information to the public. In October 1984, when we got a special, we called, somehow contacted them, and we got the data from them. At that time, agreement was become very, very good, and that's why in December '84 that I put the abstract for the Yagayama Symposium. So this is basically the true story of what actually happened at the time. So what was the lesson we should derive from it? And the reason I'm bringing this up is not to try to make the records correct, but because an important lesson has been missed here completely, which I really want to emphasize. And the first one is the in-situ measurements are critical. And they're essential for interpreting satellite data, or any kind of remote sensing data, whether it's from ground or from satellite. But we're talking about remote sensing, the nature of the remote sensing measurement is such that the dependence on prior requires you to have high quality in situ measurements. And as Susan pointed out, the remote sensing data often do not provide all the information you need. So for example, you might get a total column ozone but not get a profile, or profile may not be accurate enough. Or you do not have other species that you need in order to interpret all of the data. So in-situ measurements are really, really critical for interpretation of the remote sensing data. Without that, you really don't have that kind of synergy that you need in order to understand what is going on in the atmosphere. But beyond that, you really also need ground-based remote sensing data, such as Dawson, Brewer, SEOS, and others, as well as UMCARE and many other LiDAR, for example. Those also really play a very important role. And unfortunately, the amount of money that is going into keeping this network alive is really going down. Because some people think, incorrectly so in my view, that the satellites can take care of all of it. And that really is not true. I think we really need a healthy ground-based measurement of remote sensing instruments to be able to check periodically on the satellite measurement. So I think the main point of this should have been, and the way this all evolved, is that a robust observing system requires all three types of measurements, and it's not really competition between one type of measurement versus another type of measurement. All of those measurements came in agreement within a few months. So it's not really a big issue in science that within a few months, satellite, ground-based, and everybody all agreed that something very phenomenally important was happening over Antarctica. So I'm going to leave you at this point, and so thank you for your attention. Susan.
I have a quick one. Who came up with the word hole? Who
I think
the hole?
the best I know is Joe Farman, or at least somebody in Joe Farman's group did.
I heard it was Stolarski.
No, Stolarski denies it.
I'm not aware of it. Our first paper in '86 had that in the title in the draft, but the referee said you shouldn't use that term. So it became springtime Antarctic ozone decrease. But that may be where you got the rumor from, was that we used it and an unknown referee didn't like it.
It wasn't me.
He just showed us that the concept goes back
Yeah.
1934.
way back.
Well, but I mean, in looking at this, who first said, gee, it's a hole? I mean, somebody must have.
The rumor I heard was Sherry.
Sherry. Okay, so we have Sherry, Joe.
Well, I think in that New York Times article that you showed,
Yeah.
it says ozone hole.
I don't, it doesn't,
I think it does.
yeah.
Read carefully. I thought it did.
One of those terms when you peek in the box and let it out just a little bit.
Another question? Well, I have one actually. I was wondering, you have been comparing with the South Pole Station, but you knew that there was a tally beam.
No, we did not actually.
Yeah.
Or except for the letter that Susan and he showed, we did not get.
Yeah.
Rather, they were not archived at Toronto. The only data that we archived was from South Pole and other SOA and other places, but not having the data.
Okay, so that's a good. Okay.
So just one comment, and that's just to endorse these lessons learned. And I think we see this, I mean, this is with respect to the ozone hole, but we've seen this time and time again with respect to other ozone phenomena. Every time you publish a paper that says there's something odd going on with ozone, the first thing you have to do is go check in situ the vertical profiles from ozone sondes or from InCare, and then you have to go check the total column against the satellite. This has happened more than once. And so this lesson, I think, is extremely important for you. I think it also is reflected in other campaigns and other oddball ozone phenomena that we've seen.
Yeah, and this is becoming even more important in the Department of Troposphere and UTLS region, because there the satellite data quality starts to degrade quite a bit. So I think that this is going to be with us for a long time. We really have to have these three types of different systems.
Yeah, if I could just amplify on that, just a bit further, avoid my having to make the statement during my talk, is that we have run into that throughout the airborne campaigns as well. You'll notice when I give my presentation later today that there was a noticeable gap in a period of time for some of the polar ozone campaigns. And at that time, some unnamed NASA leadership at the higher levels felt that, okay, you guys did this in the Antarctic, you did it in the Arctic. You know, that stuff's old technology. Those types of measurements that you're making with aircraft and whatnot, that's old technology. You know, the future is with satellites, and we can do everything that needs to be done. Fortunately, we were able to strike partnerships at the time with another program at NASA, which was the Atmospheric Effects of Aviation Project. And we fostered new instrumentation. We did some combined campaigns. And then, partnered with, as you'll see, a number of European campaigns to go back to the polar regions. But, this is such an important lesson. We really need to not just pay attention to what's happening with ozone, but I think it's critical as we move into the entire climate arena.
Yeah, I totally agree with that.
Okay, thank you. So we are continuing with the talk of John Pye about the Arctic campaign.
Thank you very much, Sophie. And again, I want to echo the thanks that other speakers have given for the opportunity to speak at this meeting in front of a lot of people who I've known for quite a long time. It's a real privilege. And I know Neil, who unfortunately is unable to be here, thinks the same thing. I wasn't going to say this, but when I saw, I was in Champagne region of France last week doing some in situ sampling. And, I saw 2 black swans being caged. some photographs. I don't quite know how rare they are, but it was interesting.
Did that correlate with the sampling?
The observations of the swans were daytime. The other thing I wanted to say was really again to reiterate things that have already been said. Hervé said this morning about the importance of collaboration. And I think everything that I'm going to say emphasizes the role that collaboration within Europe played in addressing some of the important questions that people have been talking about. And Susan talked about the excitement of this area of science, and again, something for me, the excitement of the area, the fun that I've had working with a really interesting scientific problem and some really nice people, and the friendships that are developed. These are all things that, to me, are crucially important. So, Sophie asked me to say something particularly about the European Arctic and the campaigns in the European Arctic. Neil and I put this together. Jean-Pierre Pomeroy, I also acknowledge, as providing me with some of the information that has gone into this, and Jean-Pierre is going to say more after lunch. So, there was a decade of concern following the Molina and Rowland paper about possible ozone depletion. Then we've heard about the Nature letter from Joe Farman and his colleagues about the Antarctic ozone, and most of what we've heard this morning has been about Antarctic ozone. The basic facts, as Susan said, were established really quite quickly within a couple of years. An amazing scientific response to those observations. But the question remained, what was going on in the Arctic? Susan said, well, the Arctic is much more variable, it's warmer, and so on. And I think particularly those of us living in Europe wanted to understand whether the same kind of things were going on in the Arctic. And there were a couple of things happened. The French and German scientists collaborated in a number of campaigns that were based in Kiruna, relatively small campaigns, but they really laid the foundation for what we subsequently did, these Cheops campaigns where there were balloon flights. And NASA took the ER2 and the DC-8 to Stavanger in 1989. But these early activities in the late 80s still left a lot of questions. We still really needed to know whether we saw loss in the Arctic, which was similar to that that's in the Antarctic. There was a very important question about what was happening in middle latitudes, and of course, what might be happening about the future. And I think I might say something about the future. I call this talk some personal reflections, and the background that Neil and I brought to this was that I've been doing modelling of ozone since my thesis in the mid-1970s. So we had a kind of idea that ozone depletion, as we've already heard, would happen mainly in the upper stratosphere, shown in the top left. There might be a bit more ozone depletion in the polar regions, but it was really nothing like what was subsequently seen. So that when Antarctic ozone was observed, was reported, it came as a real surprise. But I think those models, and certainly the work that I did in Oxford, and my collaboration with Joe Haig, who was a radiative transfer expert, also made us realise that this isn't just a chemistry problem, but it is a chemistry climate problem, and that's something that, certainly in my career, I've come back to quite a lot. Neil's background, Neil did his first degree in Oxford in the UK, but he then went to Irvine and worked with Sherry Rowland, looking at ozone trends using ground-based and satellite data. And essentially Neil's thesis showed that there were statistically significant reductions in ozone in the middle to high latitudes of the northern hemisphere. And it posed the question of, could that ozone loss be in air which has somehow been processed in the cold Arctic and got out to middle latitudes? So that was, if you like, the personal background that we were bringing to this. There was a political background as well, of course, in that the Montreal Protocol came into force in 87. The European Commission decided that it really ought to do something in a coordinated way, and we owe a debt to Heinz Ott, who was really instrumental in helping the scientists to get together, to work together. And over a couple of years, eventually what happened is that we created an ozone science panel reporting to the European Commission. The chair of that was Gérard Mégy, massively missed, hugely, a really good scientist, of course, but also politically incredibly astute, and I think, he's been a personal friend, very badly missed. We also set up at the same time this European Ozone Research Coordinating Unit, which was chaired for a very brief period by Tony Cox until he went to a job at NELC and then came back to Cambridge, and then subsequently by me and then by Neil Harris, but we were all working together in that. And the idea, the fundamental idea, was to say there's a lot of European science going on in the area of stratospheric research, but it's rather fragmented. We didn't have a massive resource in the way that, for example, the ER2 is a laboratory that could be used by lots of Americans. So what we had to do was to coordinate the activity that was going on within Europe, to bring it together, to make it something which was actually greater than the sum of the individual parts. And that collaboration Europe-wide is something that even people in Britain still think is actually worth fighting for. In October 1990, we had the first of a series of European workshops European ozone workshops at Schliersee in the Alps, just south of Munich. Again, this was the time, this was actually the week of German reunification, so again, a nice metaphor for collaboration, I think, there. And one of the things that we talked about was the need to put together a field campaign to try to understand what was going on in the Arctic. And that came to fruition in 1991-92. We had a campaign called European Arctic Stratospheric Ozone Experiment, ESO. The Cambridge people chose the acronym, not realizing that the French couldn't really pronounce ESO. It had to be EASOE. But the collaboration's got better, and the French chose subsequent acronyms, so that was all okay. And we had a core group of people who essentially organised the activities for this campaign. And you can see the names there, many of them still very active in the field, but including Joe Farman and Gerard, and Pierre Foucault, all of whom very unfortunately are no longer with us. So, what did we try to do? As I said, what we had was a lot of individual activity, and the point of the campaign was to bring together every single strand of the stratospheric research that we could possibly do to address this issue of what was going on in the Arctic. We had a centre of activity which was in Kiruna, where we flew balloons, and we flew a lot of balloons. I'll say more about that. But we had a large number of ground-based stations that were measuring ozone, flying sondes to measure ozone and particles. So we had a range of activity, and our idea was to build up this pan-European-wide picture of the way that the Arctic stratosphere changed during this period from November 91 to April 92. There were more than something like 300 scientists involved. There was a collaboration with the Russians that, again, Jean-Pierre was instrumental in really setting up. You've seen already some 16 ground-based stations. We flew ozone sondes from something like 22 European sites with more than 1,000 ozone sondes funded by the Commission and by national agencies that allowed us to build up a picture of ozone. Christos's ozone mapping centre was heavily involved in that, in pulling together the ozone common data. So a variety of activities at these ground-based stations. Plus, we were also funding laboratory chemistry modelling, and there was a strength in Europe in modelling that developed during that period, and the central database in Oslo at Lima. A number of aircraft flew. Actually, in the first campaign, there were 3 aircraft: the DLR Falcon, yes, which is on the left there. On the right, the French Arat, and the Germans flew a Transall. These were mainly making remote sensing measurements, but there were some in-situ measurements as well. In subsequent campaigns, the Swiss Learjet also flew. We spent a lot of time working with our colleagues in Sweden. As I say, we were based, the hub of the activity was in Kiruna in northern Sweden, and the Swedes actually built Arena Arctica, which is this massive hangar that many of you will have seen. They built it because we were, a part of the business case was that we were going to bring a lot of science there. They use it for lots of other things too, but you know, it was built in time for our campaign. And again, it was rather humbling and rather frightening that the Swedes were spending such a lot of money on building this fantastic facility. Our strategy was, what we wanted to do during this period from November 91 to April 92 was to make a lot of balloon flights. And we particularly wanted to repeat flights of core instruments that could measure, say, CFCs or N2O, or water vapor, or NO2, to establish a kind of climatology. And of course, the advantage of balloons is that although as I say, we didn't have the sophistication of an ER2, but what we could do was to measure vertical profiles again and again and again. We flew more complex payloads with more comprehensive constituent coverage. So, for example, the German MIPAS instruments from Herr Fischer's group at that time, which could measure a lot of the nitrogen species, and subsequently, of course, has flown on satellite. Claude Camille-Perret had an instrument. Frank Arnold flew a mass spec to measure particles. So these were big payloads that took a lot of preparation, which were interspersed between these more frequently flown and somewhat simpler but really important instruments. We flew regularly ozone sondes, as I said, more than 1,000 ozone sondes, but also soundings at a number of stations to look at particles so that we could understand the PSC processes. I've mentioned the ground-based network and the aircraft. We had really superb Met support, both from the European Centre and from the UK Met Office. And as I say, I think Europe in particular developed a very strong chemical modelling element during the period of these campaigns. So let me show you just a few of the, we were in Kiruna, which is just inside the Arctic Circle in the winter. It was dark a lot of the time. We still managed to fly on one of these very large stratospheric balloons. Here's a nighttime launch. This is the kind of size of the payload. So that, some of these payloads were the size of a motor car. The late Cornelius Schiller over here, again much missed. The rather young Andreas Engel in that thing. There were no UK instruments flown at all, but this little Union Jack here contains some modelling output that I taped onto that. It flew successfully, but was actually destroyed by a leak in my laboratory when I got back to Cambridge. So here's the S range. You can see The big white flat area at the bottom, which is where the balloons were launched from. On the right-hand side, midway up, is the rocket range, which we didn't use. And you can see a balloon has just been launched and is on its way to the stratosphere. This is Jean-Pierre Pomeroy's artistic impression of the same thing. You can see the balloon going up there, and thanks to Jean-Pierre. I think this isn't during these, well, I know this isn't during these, so I think this is in our second campaign in Cézanne in the mid-90s. Absolutely beautiful day. So the large at the left is the large balloon. The little balloon on the right here is just to lift the very heavy payload off the ground so that it takes off safely. I think the temperature when this photograph was taken was minus 35 or something, but incredibly dry and fantastically beautiful. And here again is another frosty kind of day. We, as I say, it was all about coordination and collaboration. Lots of different payloads, all wanting to fly. So one of the roles that we had in the coordinating unit and in the core group was to say, well, how do we decide what the priorities are? So we had discussions every day. This is Pierre Faucon, who was the head of CNES, and again, I want to reiterate what Marie-Lise had said about CNES. Absolutely crucially important, both in terms of delivering the science, but also for what in English we say is delivering esprit de corps. They were absolutely superb. Frank Arnold, here in the green sweater, I think that's images, I'm not sure, and Ulrich Schmidt on the left there. So this would have been a MET briefing that we had every day where we discussed what the meteorological situation was, what we were planning to do. We delivered a very large amount of science, which was published first of all in this special issue of Geophysical Research Letters. Ralph Cicero was the editor at the time, and we had a lot of debate because Ralph said you're not allowed to have a country flag on on an AGU journal. But I don't think they realised that this was the European Union flag, so we managed to get away with that. Bottom left, you can see lots of pictures of PSCs, and again, I'm not going to say very much about it. Bottom right is the polar vortex, which I will say a little bit more about because the vortex in the Arctic is much more variable, much more complex than in the south, and a lot of our science is about trying to understand that. So here are just a few data from that ESO campaign. In the top left are data collected by Ulrich Schmidt's team. The solid line, they're all measurements of, actually I don't know whether that's N2O CFCs, doesn't really matter. The solid line in each case, in each of the panels, is a mid-latitude profile. And what you can see is that all the data that were collected when we flew inside the polar vortex had much lower values. So the air had gone higher and was much older, and it wasn't mixing in from mid-latitudes. So by flying again and again and again, we got that picture. The Ovales, who were measuring water vapor in this campaign, saw the same amount of water vapor every single time they flew. So we weren't seeing the kind of massive dehydration that was going on in the Antarctic. Things were different. The situation in 91-92 was that in early 92 it got very cold. There was a blocking anticyclone over the Atlantic, which essentially meant that air flowing around the vortex in this way was rising and adiabatically cooling. It got cold enough for polar stratospheric clouds to form, and we'll see in a minute that there was some activation. We ran calculations, so this is Glenn Carver's work down here, where he said, let's look at the cone area and see where that cone area gets to by running trajectories, and essentially this stuff was being stripped off the vortex and out into middle latitudes. The NPL data during the ESO campaign showed that during a low temperature period in the beginning of January, the column of HCl, they were measuring column HCl at a place called Ore in central Sweden. Column HCl dropped dramatically, and column CLO increased dramatically, consistent with the heterogeneous chemistry that Susan talked about. So those campaigns established some of the basic facts about the vortex. We then had a whole series, and I've not really got time to talk in much detail about them, but in 94, 95, we had a campaign called Sésame, a French acronym, where we looked both in the Arctic and in the middle latitudes, about the same number of balloons again, several aircraft, again Jean-Pierre got Concorde to fly so that we could measure the exhaust, the contrails from Concorde as part of trying to understand PSCs and so on. Ongoing, I'm going to say something in a second about MATCH. Ongoing was this intensified ozone sounding operation. In 1996, the Russian geophysical aircraft with a lot of European instruments on board flew from Rovaniemi. So this is an aircraft with capabilities somewhat like the ER-2, certainly very high flying. We had a third campaign in 1998. I think Fazeo was Bruno Cauli's idea, so an Italian acronym. And then in 2000, we collaborated. The Americans were also in Kiruna, so we had this Solve Fazeo activity with a lot of things going on. Now let me just summarize some of the results of those campaigns. So what we did do was to establish that ozone loss was occurring. This is the MATCH activity that Peter van der Garten and Marcus Rex developed with lots of other people. We had a very large number of ozone soundings from lots of different sites, and the aim was to try to connect sites where in the top left there, you launch an ozone sounding from, say, Ny-Ålesund in Spitsbergen, and if you think that the air passing trajectory followed by air that you might have measured over Ny-Ålesund crosses another site, you can trigger the launching of a second balloon, in this case at Södenkima. Can I have some water, please? Thank you. Yes, so the idea here is that Ny-Ålesund and Södenkima are connected by a trajectory of several days, and if there's been ozone loss, you might be able to see that at Södenkima. Well, you certainly wouldn't see it if you just had one flight, but if you have a very large number of these matches, then statistically you might be able to start to infer ozone depletion, and that indeed is what they did over here, where you can see ozone depletion rates on the order of some tens of ppb per day. So that was one way that ozone loss was inferred. Here's another figure which I think is really interesting. It comes from the DLR group. They were flying a LiDAR on the Falcon. This is December 94, January 95. They measured ozone, but they also measured particles. So as they flew into the vortex, then the vortex was essentially much cleaner of particles compared to outside the vortex. So this is the inside vortex region in late December with ozone values on the upper 3 to 4 parts per million. When they flew back to Germany at the end of January, again we're looking right inside the polar vortex, and now the numbers are down in the 2s of parts per million. So a demonstration that not only had ozone disappeared from inside the vortex, but that it was happening essentially ubiquitously within the vortex. Jean-Pierre has made, with colleagues in France, they've been measuring ozone using column data from, from lots of different sites, and combining that data with models, they've come up with a climatology, if you like, of ozone depletion during the period. So ongoing work, which is a heritage of the development of these campaigns. and here is Jean-Pierre up in the Arctic. The numerical models that we have access to in Europe have been really good. So a lot of people, this is some work that I published in Faraday Transactions that I think 3 people have ever read. The heavy lifting for this was done by Martin Chipperfield, who we'll be talking tomorrow. Frank Lefebvre was doing the same kind of things here in Paris. There were people working with ECAM, developing these models that Susan talked about, where you force your model with the observed analyses, meteorological analyses, and you can see the kind of structure that you reproduce, which is fantastically detailed here, but rather what's really important is that you're then capable of capturing observed detail at really fine scale. And the 2 figures on the right, you probably can't see them massively clearly, but they basically show agreement, actually in the southern hemisphere, between CLO measurements and the model. The CLO measurements being made in this case by the ER2. So we ran these models, and this is from 2000 during the Solon Fazeo campaign, when the temperatures in the Arctic vortex got very low. Temperatures were low, and you can see the blue area of low ozone right in the center of the vortex. You can see the higher values around the edge of the vortex. You can see stuff being stripped off into middle latitudes, called the center picture. And there's a strong contrast between the center of the vortex with low ozone, the outside of the rim of the vortex with high ozone loss initiated by low temperatures. This is 7th of March 2000. And this perhaps shows it rather better. This is a paper that Bjorn Martin Sinuba published with a number of us involved. We're looking at ozone at 20 kilometers. We're looking at Ny-Ålesund. We're looking at time running from November of 1999 to April 2100. The little circles are ozone soundings. The solid line is the model, which captures rather nicely the increase in ozone up to January, and then this rapid decrease that occurred subsequent to that. The thinner line is the model which was run without polar chemistry happening. And you can see the difference between the thin line and the thick line, which is the impact of polar chemistry, accounts for something like 70% depletion at that level. So this was one of those winters in the Arctic with big ozone depletion. And those models were also allowed us to look at what was going on in middle latitudes. The red and the blue data are ozone anomalies by year, and you can see this downward trend in ozone, but with a lot of variability on top of it. And what we did is we used the model to say, actually, a lot of this variability, it comes back to what Susan was saying, a lot of this variability is due to dynamics. You know, it's forced by dynamics. This was a message that when we first tried to publish this, wasn't universally acclaimed by the community. I'm delighted to say that, I think what we were able to show ultimately, and Martin may say more about this tomorrow, is that the changes in ozone in the mid-latitudes are driven by dynamical variability, by in situ loss, and by transport of ozone-depleted air from the Arctic vortex. So just to summarise, 2 things. I think the coordinated European activity did build a community of researchers who got on with each other, who respected each other, and who understood that collaborating was the best way of moving forward. And it subsequently laid a foundation for much improved understanding and the contribution that European scientists have made to the Montreal Protocol. We learned a lot, of course, about the science. We characterised the polar vortex, improved understanding of PSCs, ozone loss determined by lots of different techniques, understanding of mid-latitude loss. Actually, I didn't mention tropical work, which has also been done through Europe. So in my last couple of minutes, I'm just going to show you, so this is some of the balloon team from CNES who were up in Kiruna for these very long periods of time. Fantastic guys, a privilege and a pleasure to work with them. I really enjoyed my time there. That's a rather younger me in pointing to where I am. There's the little UK payload that we flew. Henri Alvarez came up to me once during one of these campaigns and he said, John, he said, can you tell me what does humiliating mean? So I explained it to him at some point. He said, that explains it. I've just seen that England were humiliated by Zimbabwe at cricket yesterday. Neil Harris, my co-author on this, unable to be here, he's learning to drink the French way over there in the left-hand corner. Pierre Faucon, who again, a man I admired enormously, a really fantastic guy, very an intellectual, a man of great good humour, and sorely missed. And of course, my friend Gerard Magie. I told the story of this photograph at his memorial in Paris. Gerard had been flying on the plane. We were all sat around in the hangar drinking German beer. As soon as Gerard walked down, I gave him the beer and then took the photograph of him and said, you know, I'll now show you this in later time, making it look as if all you were doing was drinking beer. But he'd not been on a very, very long flight. And finally, and I'll say a few words at dinner tonight about Joe Farmer, but Joe was a lovely man and a great friend and, of course, massively influential scientist. So I'd like to dedicate this to the memory of those three people who really did such a lot for these European campaigns. I'd like to acknowledge the European Commission, Heinz-Orr. You're using Georgios Amanatidis Georgios was great to work with, high maintenance, but he really had science at the heart of what he was trying to do. So Kness, Esrange, and the people who helped us in Cambridge, Helen Molyneux, Wood and Rebecca Pennies. And that's congrats.
Thank you very much, John. Other questions? We have time for questions because the lunch is not ready. So.
This was a very nice talk, and I really admired you mentioning the ground-based networks participating in the campaign. So we have campaigns where we have very intensive research and measurements. And then we have regular long-term networks. And the way how I see it in Arctic, that we are starting to see disappearance of some of these networks. What do you think the value of this long-term networks in Arctic, and how much that contributes to the science?
Well, I mean, okay, it clearly contributes in. It contributed massively in the campaign. But there is absolutely no doubt about that. Perhaps the best way to answer your, I was going to say this tonight. I think that the NELC British Antarctic Survey would probably have stopped making ozone measurements if they thought they'd have saved any money by doing it. Once they were sending people down there, they might as well do something. But I don't think until Joe's paper was published, they actually realized the value of the data that was being collected. It's just so easy to stop stuff because, well, it hasn't shown us anything yet. So it's not going to do in the future. Well, I mean, how can you make that happen? So it seems to me that EK, we have this at the end of the last thing. Ground-based measurements are essential. But you know, equally, they are, you know, I understand there's an expense associated with it, but we just have to keep fighting for it.
Thank you. Another question or comment?
I guess just a general one. There's been lots of controversy for years about how well the models could actually simulate Arctic ozone loss. Just in in broad terms, do you want to comment on the state of the art of that? I mean, one interesting question is how important are the short-lived molecules? How important are the short-lived compounds? Bromine? I mean, is it all just a transport mismatch? What's your current thinking on the model data comparison? Where does it point us?
Well, that's a very broad question.
Not an easy one.
Yeah, I think I guess, I'm going to sidestep your question by, in a sense, my philosophy of modeling has been to say, can we understand processes that we're going on? Can we use models, a combination of models and data, to understand processes? And I think at that level, although there are differences between different models and differences between different techniques for deriving ozone depletion, then I think we say, we've actually got a pretty good understanding. That the differences are largely, they're not first order. So I think we're in good shape there. Your question about the short-lived compounds is a slightly different question. But I think the story of the short-lived compounds, from my perspective, and I know Rainer Saini's paper has raised a lot of people are very excited about that. It's about saying, here is something that you need to keep an eye on. It's not really saying, in 2050, this is going to happen. It's about saying, here is something that could potentially upset the apple cart if we don't start thinking about it. So you use the model to inform the community, but also to inform the process, to say, here are things that you need to be thinking about. So I've never got too hung up on model. In fact, I usually say to my students, when the model and the data don't agree, that's when it's really interesting. I've sidestepped the question a bit.
John, I have a comment also on the fact that in the first campaign, there was the peanut tuber also aerosol, which were also, that was a problem for the instrument, some of the instruments, because they could not really well measure ozone, but it was also very interesting because we could see also how the peanut tuber aerosol penetrated the vortex and what was the difference between the Antarctic and the Arctic. I remember because we made this slide on ARA and we could see the PSC above the aerosol layer.
No, I mean, so peanut tuber had gone off in the summer before, and it's true that the sunsets that we got in the northern hemisphere, that made summer and subsequently were fantastic. And it certainly was a compounding factor. It probably helped us to understand some things quite well. I think some of the issues about what was going on with the NOI budget, there were more particles there to effect more change. So in some ways they helped, but I agree that there were, it was conflicting too. But of course, much less of that air got into the
Actually, I'll follow up on that.
Susan brought up the question of how well we do the Arctic. Sophie, you brought up the 91 eruption in Mount Pinatubo. They flew AASE 2 in the winter of 91, 92. And when we first flew in mid-latitudes, of course, we saw the Pinatubo eruption particles. When we went into the vortex, it was nice and clean in our first observations there. And of course, that gradually changed over the course of the winter. And so, again, going back to Susan's question, there's a nice experiment to look at to see how well you can do those in situ measurements, how well you can simulate them, and what we see actual impact of those particles on the stratosphere, the northern stratosphere as a whole, so to speak.
Susan showed a bit earlier that if you want to look at the recovery of ozone in the Antarctic, you don't go in October, you go preferably in September because you're just at the edge and there is sensitivity of ozone to chlorine. Now the Arctic is a bit at the edge in terms of, I mean, you don't have this massive ozone depletion, so there are years where you kind of, where ozone and chlorine are very sensitive to each other. So the question is, would it be easier or perhaps better to look, when we think about ozone recovery, to look maybe also at the Arctic? Or is it?
I think
it's complicated because of the dynamics.
I think the massive variability in the Arctic makes it really difficult. So if you wanted to come up with anything which would be statistically sensible, I just think it's such a long time. Yeah, it's really, really hard to do. So I think all you can do are do, what Susan described as these fingerprint studies, where you try to bring your best understanding of all the processes together and say, can we at least understand what's going on? Can we, handle this this accountability phase, if you like, as indeed Dan Albright had called it.
Okay. Thank you very much, John. So before the lunch, we still have to wait a little bit. We are going to make a group photo. So I invite you to go into the hall there, and we are going to figure out how we can make this photo together. So just don't go away, and then the lunch.